is grammar simplification. So far we have seen this context free grammar we have already seen, but now we will try to convert this context free grammar into some simplified form. Okay, for example, give you this expression x minus x plus y plus z plus 1 plus 1. If I give you this type of expression in mathematics, if someone gives you this type of equation, then what you will do, you will simplify it. Okay, you will do the simplification. So you know that okay, there is no need to put them, so you will simplify it. You know that you can do direct addition, so basically you can simplify like this: y plus z plus 2. So this thing can be simplified like this. The meaning is same. The meaning is here. The meaning here is same as the meaning here. The meaning has not changed, but you have done the simplification. Similarly, we will try to do simplification of context-free grammar. For example, if I give you this grammar, if I give you a, and this a is going to a. Let's assume if I give you this grammar. In this grammar, you can notice one thing, that this s will derive a. That is okay, very nice. Okay, s is driven a, that's okay. So now s, when s goes to a, when this s goes to a, now this a will have to go to a. Now this a, basically this a will have to again go to a. You can notice one thing, that you can never derive a string. You can never derive a string because this a will never terminate. This a will just keep on going on like this. This a will never be removed. This a will never be removed. So that's why you can see that actually you can say that this production is useless. We will say that this production is useless because it is not deriving any string. So this production is useless for us. So we will try to eliminate useless productions. This is the third thing we will do. Basically today we will do three things, and this is the third thing we will do, that we will remove these useless productions. You can see this is useless production because this a is useless, so automatically s goes to a is also useless. So you can see when we simplify this grammar, then finally we will get this grammar. You can see this is such a simplified grammar. So this is what we mean by simplification of a grammar. So what else we will try to do? So we will try to eliminate the useless productions. Okay, for example, here you can see s goes to a, okay, and a goes to a. Here you can see again this a is a useless production. Why? Because when you start in the, of course you will start from where, you will start in the beginning symbol. You will start with s, you will start in starting symbol. So when you start in starting symbol, then you can never reach this a. You can never reach this a. So because you can never reach this a, so this production, this symbol a is useless because you can never reach it. When you start with s, then you can never reach it. So you can remove because this is useless. So again the simplified grammar will be s goes to a. This is your simplified grammar. So these are the two type of useless symbols we have. The first useless symbol that we saw, that was reachable, but that was not generating any string. You can see. So this was the first type of useless symbol we saw. You can see this type of symbol we saw. Here you can see this a is reachable. This a is reachable. Okay, but this was not generating because it was not generating any string. So I will say it is not gen means not generating. It is not generating. So that's why, because it is not generating any string, so we can say that this is a useless production. And the second type of useless production, the second type of useless symbol that we have seen, that is this: s goes to a and a goes to a. Here you can see this a is generating. This a is generating because it is generating string a. So you can see it is generating string double a, but it is not reachable. It is not reachable. So because it is not reachable, so what is the use of having this? So you can remove this. So we have two type of useless symbols. We will want to remove them. We will want to remove useless symbols. What is the other thing that we can do to simplify our grammar? For example, if you have this type of production, let's assume s goes to a, s goes to a, uh, now S goes to A goes to B goes to A. Let's assume you have this type of grammar. This grammar can also be simplified, very easily simplified. See, this is just a unit production. Like from one variable, you are directly going to another variable. So from A, you are directly going to B. Okay. So this is called unit production. From one variable, you are going to another variable. So this is called unit production. You can see. Remember, this is not a unit production because here from one variable you are going to A. So this is not a unit production. This is a unit production. S goes to A. This is a unit production. This is not a unit production. So anyway, this is unit production and we will want to remove them. Why do we want to remove them? Because you can see if I remove this A goes to B, I can directly put this double A here. See, okay, from A you are going to B, from B you are going to double A. What you can do, okay, you remove this thing, you can directly go to double A. So you can remove this unit production and you can directly go to double A. Now what has happened? If you do this, then this has become this B has become useless. So you can remove it because we want to remove useless symbols. So now you can remove it. Okay. So you can see we have removed it and we have removed that unit production also. This is also unit production. We will want to remove it. So we can remove this A also. What we can do? We can replace this A with double A. So we can replace this A with double A. So again, this production has been removed because we can remove that A with the double A. Okay. So so this is the idea of having of removing the unit production. So we have removed all the unit productions. So this is the idea. Now Now, what is the other type of production that we will want to remove? We will want to remove something called epsilon production. For example, let's consider this. S goes to S goes to AA and S goes to BA. Okay, and this A goes to epsilon. We will want to remove this type of epsilon production also. Because first of all, why do we want to remove them? There is a reason. This type of production, what it will do, this type of production will do like this. Let's assume you have a complicated grammar. You have a very complicated grammar is there, let's assume, and there is a string you have, and this string has length, let's assume this string has length 6. So this is a very complicated grammar. This is a start symbol and so on. So this is your string of length 6. Now you want to see whether this string belongs to the language of this grammar or not. You want to check it. Now what you will do, you will start in the start symbol. Then you can take some production. From S you can take some production and so on. Okay. Now at some point of time, let's assume you have a sequence of variables and terminals. You have some sequence like this. Let's assume A small a, okay, B capital B. So basically you have a sequence of terminals and variables. You have a long, let's assume you have a sequence of length 7. So this is your sequence of length 7, and this sequence has variables and this sequence has terminals. At this point of time, you would expect that our string has length 6. Our string has length 6, but you have reached a, a sequence of length 7. So at least you should not go beyond that. Okay, to find this W, to find this string, you should not go beyond that. This is your expectation because your string has only length 6 and you have already reached the sentences. You can say these are called sequence. These sequences which have variables and terminals, these sequences are called sentential forms. This is called sentential forms. So what I can say, see, so these type of things where we have variables also, where we have string terminals also. You can say this is variable, this is terminal, this is variable, this is terminal. So this type of sequences are called sentential forms. Now you have already reached a sentential form of length say 7. So you would expect that you should not go beyond that. Okay. But if you have this type of epsilon production, let's assume in your grammar, if you have this type of epsilon production, then you can never guarantee, because some variables can go to epsilon, so your sentenceal form's length will decrease. I'm going to say, okay, what I'm saying like this: your string has length 6. Your string has length 6. Now, two situations you can consider. The first situation, let's assume there is no epsilon production. So there is no epsilon production. There is no epsilon production in your grammar. In your grammar, there is no epsilon production. Now let's assume that you have reached a sentenceal form of length 7. 1, 2, 3, 4, 5, 6, 7. Let's assume you have reached a sentence form of length 7. Now you can guarantee that this string will definitely not be generated from this sentenceal form, because there is no epsilon production. So each variable can go to either a or b. Okay, each variable, this is terminal, let's assume this is a variable, this can go to either a or b, because there is no epsilon production. Every production is, you can see, every variable will, no variable can derive epsilon. So every variable will at least derive small a small b, at least. Okay, maybe double a double b, but at least small a small b it will be derived. So now if this happens, then how many, you can see, if this happens, then how much length you will get? You will get more than 6 length. So you can guarantee that this string will definitely not be generated from this type of sentential form. Then what you can do, you can discard this type of sentential form, you can discard it, and then you can check something else. So this is the basic benefit, this is the basic benefit that you will get. Now, now so now let's assume you have these epsilon productions. Then you cannot guarantee, if once you reach a sentencer form of length even 10, if you reach a sentencer form of length even 10, then also you cannot guarantee, because maybe some variables can go to epsilon, some variables can go to epsilon, some variables can go to epsilon, some variable can go to epsilon. So you cannot guarantee that your string will not be generated. So this is the basic idea. Like these epsilon productions actually, these epsilon productions will will make our derivations longer. Okay, we will take a lot of time to to see whether a string belongs to our language or not, because even if you get sentential forms of length 10, then also you cannot guarantee whether you will generate that string or not, because maybe some symbols can go to epsilon, and hence your length of this sentential form will decrease. So maybe you can generate w. So that's why you can see the things will become harder for us, the things will become longer, and we will take a lot of time to find out whether this string belongs to our language or not. So that's why these epsilon productions are, we want to remove these epsilon productions. So this is the idea. Now let's see, first we will see how to remove epsilon productions from a grammar, such that of course the language of the grammar should not change. This is of course, because if the language of the grammar is changing, then there is no use. So if you have a grammar G, let's assume, and this grammar G is generating language L, you want to simplify it, and you want to get a simplified grammar, such that this grammar also generates language L, but this is a simplified grammar. In this grammar you do not have epsilon production, in this grammar you do not have unit production, in this grammar you do not have useless symbols, useless productions. So that's why this is the simplification. Of course the language should not change. So now the first thing that we will see is okay, first of all, why do we want to do this simplification? The simplification we want to do because of this reason. Because if your string belongs to the language of G, then basically you want to find out whether this string belongs to the whether this string can be generated by the grammar or not. This thing you want to find out, and when you want to find out, then these type of things like useless symbols, like epsilon productions, these type of things are going to make your things, make your process harder. Okay, these type of things will make your algorithm very inefficient. it will take, your algorithm will take a lot of time. If in your grammar there are useless symbols, there are unit production, there are epsilon production. So that's why we want to simplify our grammar, so that our this process of finding out whether a string belongs to the language or not, this process becomes simple. So that's why we want to remove them. So let's see how to remove them one by one. First we will see how to remove epsilon production. If you have a epsilon production, then how will you remove it? So first of all, to see the algorithm to see the algorithm of this how to eliminate these epsilon productions, first we will see what is something called nullable symbols. What is a nullable? Nullable means a variable which can go to epsilon. A variable which can go to epsilon, this type of variable is called nullable variable or nullable symbol. So first we want to find out these variables which actually can go to epsilon. So first we will find out these, and then we will remove these epsilon productions. So let's see, first let's see how to find out them. Okay. So how to find out nullable variables? Nullable variable means a variable which can eventually go to epsilon. For example, you can see, you can take this example, s goes to a, s goes to ab, a goes to b epsilon, and b goes to c epsilon. This, in this grammar you can see, directly you can see this a is nullable, directly you can see this a is nullable, directly you can see this b is nullable. But remember, s is also nullable. S can go to ab, a can go to epsilon, b can go to epsilon. So you can see s is also nullable because s can also go to epsilon. So all these things are nullable here. Okay, so we want now, once we have found out what are the nullable symbols, now we want to remove these type of null productions. These are the null productions that we want to remove. So what is the algorithm? The algorithm, first it will find all the nullable symbols. So you can very easily find the nullable symbols very easily. See how to find nullable symbol. If you have direct production, this is called direct production. If you have direct production of this form, then clearly you can see this a is nullable. So you, what you do, you make a nullable. Now you find basically all the direct productions which are for example, if you have this type of direct production, then this b is also nullable. Now what you do, you find out this type of production. You find out this type of production where all the variables on the right hand side are nullable. A is nullable, b is nullable. If this is happening, then s is also nullable. So this is how you can find all the nullable variables, all the nullable symbols you can, this is how you can find them. Once you have found the nullable symbols, then what you can do, let's see. This is a very simple algorithm. This is a very intuitive algorithm. Let's assume you have this grammar. S goes to a, AB, A goes to B epsilon, and B goes to C epsilon. Let's assume you have this grammar. In this grammar, first of all, you what you will do, you will find all the nullable symbols. So you can see this a is nullable, this b is nullable, because of these direct null productions. These are the direct null productions. So because of them, you can see this a is nullable, b is nullable, and because of this, here you can see both a and b are nullable, both a and b are nullable. So automatically s will also become nullable. So these are your nullable symbols. Once you have found the nullable symbols, then what you will do, just see all the right hand sides. For example, here you can see this a is nullable. So what you will do, okay, first of all, see, first of all, just directly add a new symbol as dash. First of all, directly add a new symbol as dash to us. Okay, when you are removing null productions, then this you can directly do. Just add a new start symbol as dash goes to s, directly add it. Okay, now what you can do, after adding this you can just directly add. And after adding this, what you do, see, this a can go to epsilon, this a is nullable. What it tells you, this a can go to epsilon. So what you do, you keep it as it is and you take it to epsilon. So are you getting this point? See, this a can go to epsilon. So how do, you just write it as it is, and you send this a to epsilon, so you will get this. So this is how you do. Now just see this. This is saying that ab. So what you do here, write it as it is. Now this a can go to epsilon, so send it to epsilon. This b can go to epsilon, so send it to epsilon. Now both of them can go to epsilon. When both of them can go to epsilon, just don't put null production, because you want to remove null production. So don't put it again. Okay, so don't put it again. So this is enough. So did you get it? See here, these are two nullable symbols you have. So what we have done, we have put them as it is. This a is nullable, so we have removed a, so we will get this b. This b is nullable, so we have removed b, so we will get a. So this is how we made it. Now let's see here. A goes to B, that is okay. Just remove this null production. Just directly remove this null production. And B goes to C and remove this null production. So this is how you will get your simplified grammar. But one more thing, because this s is nullable, so just add like this. In this new start symbol, just add this. So you can see this null production you cannot remove. This null production, because this null production will give you the null string in your language. If you remove this, then in your language you won't get the null string. Okay, so of course, if your language contains null string, then you definitely want to have this at least this one null production you cannot remove. This is the only null production that you cannot remove. If your grammar generates empty string, then for example here you can see the grammar that we have taken. This grammar generates null string. How do we know? Very easily, because this as starting symbol is nullable. When starting symbol is nullable, then you can say that your grammar can generate empty string. So what you do, when your s is nullable, then you add this production as dash goes to epsilon. So this is how you can remove the null productions. This is how you can remove the null productions. Let's try one question. You can try this. S goes to SAA, SAB, A goes to small a epsilon, B goes to try this question. So apply the procedure. First you find out nullable variables, then you apply the algorithm. Very simple algorithm is there. Just take your copy pen and just try to apply it. Once you are done, let me know. So let's do one thing. Let me do this question and you can try the next question. Let me explain this question. Okay. So let's first we will find nullable variables. Let's see what are the nullable variables. Directly you can see this a is nullable. This you can see directly. Directly you can see this b is nullable. So this b you can see directly. Now a and b are nullable. This you can see directly. Now just check out whether anything else is nullable or not. This s is nullable or not? No, this s is not nullable. You can see this s is not nullable. Let's add one more production here. Let's add one more production here. S goes to A. So you can see, first of all, this S is not a nullable. Why? As I told you, so you have found all the direct nullable productions variables. This A is nullable, this B is nullable. Now this S is not nullable, because you can see in this S, you can see there is no such production in which all the symbols are nullable. Here you can see A is nullable, B is nullable, but this S is not nullable. So you can see S is not nullable. So these are your nullable symbols. Once you have found out nullable symbols, now you don't have to do anything. Just directly add a new starting symbol. S dash goes to S. Just add it. Add this new starting symbol. S dash goes to S. Now this S will go to where? A second. This s dash will go to where? This s is not nullable, so this s you will leave as it is. This a is nullable, so you will write it as it is and you will send it to null. Are you getting? See, in this production, this A is nullable. So what you will do, you will write it as it is and you will send it to null. So two times basically. Write it as it is and send it to null. Let's see here. Here two nullable variables are there. This A and B, these are nullable variables. So what you do, you write it as it is. This A is nullable, so send this A to epsilon. This B is nullable, so send this B to epsilon. You can see here. This B is nullable, so you can send it to epsilon. This A is nullable, so you can send it to epsilon. Both these A and B are nullable, so you can send both of them to epsilon. So this is how you will get. And this A. Both these A and B are epsilon. So you can see basically total four cases are there. One time you are not removing AB, another time you are removing A, another time you are removing B, another time you are removing both A and B. So this is how you can get. Now let's see this A. So this A goes to A, that is okay. Just remove this null production because we don't want null production, so remove it. And here you can see this B is nullable, so write it as it is and remove this B because this B is nullable. So write it as it is and remove and another possibility, remove this B. Now B goes to just remove this null production. Here you can see write it as it is and this B is nullable, so remove this B. So this is how you will get, this is how you can remove the null productions. You can see all the null productions have been removed. So this is your null production removal algorithm. So now you are ready to anyone has any doubt, then you can ask, else you can try this example. So try this example. S goes to, if you have any doubt, then you can ask. S goes to A, B, C, S, B, D. Try this question. Try this. Once you are done, let me know. Okay. What are the nullable symbols, Sanjeev? What are the nullable symbols, Aditi? Right. So now let's see. First, we will find the nullable symbols. What are the nullable symbols? So you can see this is directly nullable symbol. This A is directly nullable symbol. B is directly nullable symbol. C is directly nullable symbol. D is directly nullable symbol. C, D. All these are directly nullable symbols. Now let's come to s. This is the remaining symbol. Let's see whether it is nullable or not. You can see it is not nullable, because to make this s nullable you need some production here where every variable is nullable. You can see here, of course there is a terminal, so you can't make nullable. Here you can see this bd are nullable, but s is not yet nullable. S is not yet nullable, so this is also not nullable. You can see these are your nullable symbols. Once you have done this nullable symbols, now you can very easily do this. What you will do, first of all you will add a new, what you will do, you will add a new variable s dash goes to s. Remember, you don't have to add this because s is not nullable. This epsilon production we add only when s is nullable. S is not nullable, so we won't add that epsilon production. So we will get s dash goes to s. Now here you can see a b c, everyone is nullable. So what are the productions you will add? You will leave them as it is. Also you will leave them as it is. Also what you will do, you will remove this a, you will remove this c, sorry b, you will remove this c. Now you will remove both a and b, you will remove both b and c, you will remove both a and c. Now you will remove everyone. So you can see these are the productions you will add, because a b c all are nullable. So one time you will leave them as it is, another time you will remove a, another time you will remove b, another time you will remove c, another time you will remove both a and b, another time you will remove both b and c, another time you will remove both a and c, and another time you will remove a b c everyone. Similarly here b and d are nullable, so you will leave them as it is. Another time you will remove b, another time you will remove d, another time you will remove both of them. So these are the productions you will add. Here coming to here, you will just remove this, remove this, remove this, remove this. You will remove these productions. So this is your grammar that you will get. So this is how you can eliminate the null productions. So I hope that you got this algorithm. So this is how you can find nullable variables. Once you have found nullable variables, then you can apply this procedure. Okay, so this is your procedure. You can just go through this procedure after this class is over. I will share the slides. And now let's try to answer this question. He has given a question. This is the original grammar. S goes to ab, a goes to a, or c. No, that is epsilon. That is epsilon. I think that is epsilon. Wait a second. Yes, that is epsilon. And b goes to b epsilon. So just try on this grammar. Oh, okay, let's I think you have got it. So then let's see what are the nullable symbols. You can see a is nullable because of this direct null production, b is nullable because of this direct null production, and just go to s and check. You can see this a and b both are nullable, so s is also nullable. So every symbol a b s, every symbol is nullable. Now what you will do, first you will add a new production. First you will add a new production, s dash goes to s. Now because this s is nullable, so you will add like this. So you can see here, so you will add this production. Now what you will do, after adding this production, you can see both a and b are nullable. So what you will do, you will leave it as it is. You will remove this b, you will remove this a, you will remove both of them, but don't remove both of them, because if you remove both of them, then you will get epsilon. So you don't want to get epsilon because you want to remove epsilon production. So just don't do it. Basically you don't want epsilon productions, you don't want null productions, so don't keep it. Anyway, let's come here. You can remove this null production directly, and here you can see a is nullable. So what you will do, you will leave it as it is. You will remove the first a, here you will remove the second a, and here you will remove the every a. You can see, so basically you will remove the first a, in the second turn you will remove the second a, in the third turn you will remove both the a's. Similarly b, you will leave it as it is. You will remove the first b, you will remove the second b, you will remove both the b's, and of course this epsilon you will remove. So this is how you can apply the null production removal algorithm. Okay. Now let's see how to eliminate unit productions. So this unit production, what is a unit production? This type of productions are unit production. A variable is going to variable. This type of production are called unit production. So how to remove this type of production? Very easily. Actually, don't have to apply the algorithm. You can just directly do it. What you do? Let's take one example. Let's assume you have this type of situation. Let's assume you have S goes to A A A. A goes to small b, b, b. And this small b goes to, let's assume A, A. Let's assume this is the situation. Here you can see you have unit productions. This is unit production, this is unit production. Okay, so S is going to A, this is unit production. A is going to B, this is also unit production. Okay, now what you will do, you want to remove this unit production. See, this B, this A goes to B, this A goes to B. This is saying that, what it is saying? It is saying that basically A is going to B. So when you want to remove this unit production, then what you can do, this A can go to B. Now this B can go to double A. So when you remove this B, then what you can do, you can add these things here. You can add these things here. Now you can remove B. Basically, add everything that B can derive, add everything that B can derive here, and then remove this B. Similarly, this S goes to A, this is also unit production. So what you do, when you remove this A, then add everything that A deriving, add everything here, add everything here. Okay, so this is how you can solve it. So this is how you can remove the unit production very easily. Just when you are removing a unit production, then what you do, you put everything that that symbol is deriving, you put everything on the RHS. So this is how you can remove the unit production. For example, you can take this example. S goes to AS, and A goes to BA, BB, and B. B goes to small a, small capital B, small b. Let's assume you have this type of grammar. Now, if you have this type of grammar, then what you will do? Again, you can remove the null productions. See, first of all, when you are removing the null production, then you can see first thing. From S, there is a null production like this. S goes to A. This is unit production. Unit production. S goes to A. This is unit production. This A goes to B, this is also unit production. You can see S goes to A, this is unit production. A goes to B, this is also unit production. So S goes to B, this is also unit production, because S can go to A can go to B. So what you can say, S is going to B, S is going to B. This is also unit production. When you have this type of situation, then what you do? First you handle this, then you handle this. This is how you should do. So what you will do? First you will handle this unit production. So when you remove this unit production, then what you will do? Add everything that this B can derive, add everything here. So put everything here that this B can derive, put everything here. Now you can remove this unit production. When you remove this unit production, then what you can do? Whatever this is deriving, put everything here, basically put everything B, basically put everything and then remove this unit production. So this is how the unit production elimination algorithm works. Okay, so this is very intuitive and easy algorithm. You can just directly use it. Now we will see how to remove useless productions. So how to remove useless productions? Now, useless production, I told you, there are two types of useless productions we have. First is which are not reachable, and another is which are not generating any string. Two type of useless symbols we have. Okay, so we want to remove both of them. So first we will remove the not generating so okay, what we will do, first we will remove the not generating type thing, the symbols which are not generating any string. First we will remove those useless symbols, then second we will remove those useless symbols which are not reachable. So in this order we will do. First we will remove those useless symbols which are not generating any string. Second, we will remove those useless symbols which are not reachable. This is how we will apply this algorithm. And this again is a very easy algorithm. You can very easily you can do this. For example, S goes to A B. Okay, slash epsilon. A goes to small a capital. Let's assume small a C D. C derives something called A or AC, and D goes to AD. Let's take this example. In this example, you can see what are the useless symbols. Let's see what are the useless symbols. See, useless symbols means two types of symbols are useless symbols. One that is not reachable. Here everything is reachable. You can see here A is reachable, B is reachable. Because A is reachable, so C and D are also reachable. So every symbol is reachable here. But some symbols are not generating. Let's see what symbols are not generating. You can see this symbol is not generating. D goes to AD. So this D is useless because this is not generating. So what we will do, we will remove those symbols which are not generating. So this D is useless. Because this D is useless, so automatically wherever you find this D, that is also useless. So this is also useless. So are you getting this point? See, this D is useless because it is not generating any string. So now you can remove this useless production. This D is useless. So because this D is useless, so this CD also becomes useless because of D. So you can remove this also. Now if you remove these two things, now this C becomes unreachable. Now this C becomes unreachable. So now this is also useless. That's why I told you, first you remove the not generating symbols. So you can see here D is not generating symbol. So first you remove not generating symbols. Then you remove unreachable symbols. So we have removed not generating symbols. After that we have removed not reachable symbols. So this also will be gone. This also will be gone. Finally, this is your simplified grammar. We have removed all the useless symbols. And also, of course, now of course there is no B here, you can see. So this also becomes useless. There is no B here. Okay, because in this grammar there is no B. There is no B. There is no, you can see. So this B is also not generating. So this also goes like this also becomes useless. Once this becomes useless, then A will become useless. So it also becomes useless. Finally, what you will get, the simplified grammar is only S goes to epsilon. This is your simplified grammar. You can see how much simplification you can do once you remove these three things: null production, unit production, useless symbols. These things once you remove, then you can do a lot of simplification. So this is the idea of simplifying a grammar. Okay, and in which order you should do? Remember, whenever you are simplifying a algorithm, a grammar, okay, then you should apply. Whenever you are doing all these three things, let's assume you want to remove null production, you want to remove unit production, you want to remove useless symbols, then in which order you should apply these algorithms? So this is the order in which you should apply these algorithms. First you remove null productions, then you remove unit production, then you remove useless symbols. Remember, in this order you should do, because if you change the order, then what will happen? Let me tell you what will happen. When you remove null production, then these things can occur. When you remove this null production, then unit production can occur. Let's assume there is no unit production, but once you remove this null production, then unit production can occur. Similarly, when you remove this unit production, then useless symbols can occur. So that's why you should apply in this order. Let's assume you change the order. First you apply the unit production removal algorithm. Then what will happen? First you do this, then if you do this, then you will again have to do this. That is the problem. Because once you do this, then some unit productions will occur. So then you will again have to do this. So it will be a double work. So what you have to do, basically just apply in this order you apply. Once you apply in this order, first you do this, then you do this, then you do this. If you do in this order, then you don't have to do anything twice. This order is best order, and you if you change the order, then you will have to again do the same thing that you have done. Okay, so anyway, this is your simplification of algorithm. So basically you should apply in this order: eliminate epsilon production, eliminate unit production, eliminate useless symbols. You should do in this order. Okay, if you do not do this in this order, then you can see that, for example, once you do this, let's assume directly you are removing useless symbols. You have already applied the useless symbol remove algorithm, then you are removing null production. When you remove null production, then automatically some useless symbols can again come. So then again you will have to apply the useless symbol removal algorithm. So you can see there is a double work here. So you don't want to do the double work, so you just follow this order. So this is your grammar simplification. Now we will see something called Chomsky normal form. See, when you have this CFG can have an ugly structure. Ugly. What do I mean by ugly? For example, it can have any ugly structure. Any ugly structure it can have. Okay, anything like, okay, so very complicated structure it can have. Okay, you can see any complicated structure it can have, because you know in CFG we do not put any restriction on the RHS. Here we do not put any restriction. We only put the restriction on the LHS, that every LHS, on the LHS of every production you should have exactly one variable. This is the only restriction we put. You know this thing. So this CFG can have very ugly structure. So what we do, we sometimes, if we can do, then we want some beautiful structure we want. So every CFG actually can be converted into something called CNF form, Chomsky normal form. If you have a CFG, then this CFG can be converted into Chomsky normal form. This Chomsky normal form has a fixed structure. Like every production has to follow some fixed structure. Okay, so that's why this CNF form, because it has a fixed structure, some beautiful and very, you can say, specific structure. So it is sometimes useful when you are writing algorithms, when you are doing some manipulation, when you are making a parser. Basically when you are doing something, then instead of this random thing, this CFG is a very random thing. You can have anything in CFG on RHS of the production. On the right side of the production you can have anything. So what you need, sometimes you need this type of you can say this type of beautiful structure. So every CFG, if you have a CFG, let's assume you you have a CFG. Let's assume this is the language L. So this grammar is generating language L, and this is your CFG. Then what you can do, you can transform this CFG into CNF form, into CNF form, into CNF form. So into this CNF form, such that language still is L. Language should not change. So every CFG can be transformed into CNF form. This is called Chomsky normal form. Now, what is the Chomsky normal form? This is a beautiful form. You can see very fixed structure it has. So only these type of productions you can allow. So basically in Chomsky normal form, you only allow these two type of productions. Variable can either go to a terminal, variable is going to terminal, or variable can go to two variables. two variables. So this is the structure that you allow. Basically, every production should follow these two rules. You cannot have any random production. No, you cannot have. These are the rules you should follow. Every variable. So this variable can either go to terminal, or this variable can go to two variables. This there is an exception. There is an exception, and that is uh, for the starting symbol we make an exception. For the starting symbol we allow s goes to epsilon. We allow this. Why do we allow it? Because sometimes language contains the empty string. Okay, so sometimes language contains the empty string, so that's why you allow this s goes to epsilon. But there is a condition here. So what is the condition here? That whenever you are writing this type of production, these variables cannot be starting symbol. Okay, let me compile everything. Let me compile. Chomsky normal form will allow what type of productions? So this type of production is allowed. Variable is going to terminal. This is allowed. Variable is going to two variables. This is allowed. But here there is a condition that these two variables, they cannot be starting symbol. B cannot be starting symbol. C cannot be starting symbol. So this is the conditions. B, C, they cannot be starting symbol. So these productions you allow. If this is the starting symbol, then you allow this type of production also, because we want sometimes our language contains empty string, so we want to generate empty string, so you allow. So these are the things you allow. Remember, this null production you are allowing only for the starting symbol. For the starting symbol you are allowing this null production. For any other symbol you are not allowing this symbol. So anyway, this is the condition. You allow this type of production. A goes to terminal, variable goes to terminal. This is allowed. Variable goes to two variables. This is allowed, but the condition is that these two variables, they cannot be starting symbol. For the starting symbol you allow s goes to epsilon. This is allowed. So so these are the things that are allowed in Chomsky normal form. Now every grammar can be converted into Chomsky normal form. Every grammar. When you convert a grammar into Chomsky normal form, then the first thing that you need to do is simplify it. Before you convert your grammar into Chomsky normal form, into CNF, before that you need to simplify it. So you need to remove null production, you need to remove unit production, you need to remove useless symbols. So basically the procedure to convert into Chomsky normal form is like this. If you want to convert a CFG into CNF form, then what you will do? You will first apply removal of epsilon production. You will remove them. You will remove unit production. You will remove useless symbols. And after that, you will apply the transformation into CNF. After that, you will apply the transformation into CNF. So first you need to do these things. Now let's take this example. This is your original grammar. You want to convert this grammar into CNF. Okay. Okay. Let me tell you. You already know how to remove null production. You already know how to remove unit production. You already know how to remove useless production. Once you have done these things, then how can you convert into CNF form? Let me tell you that. Very easily you can convert. Let's assume after removing null production, unit production, and useless symbols, after removal of these things, you are getting this type of production. Let's assume you are getting this type of production. Also, if you are getting this type of production, then there is nothing to do. Nothing to do, because this is allowed in CNF. So there is nothing to do. If you have this type of production, A goes to AA. Now this is not allowed in. This is not allowed. You can say this is not allowed in our CNF. Then what you will do? What you can do in CNF, it is not allowed, but it is allowed that what you can do, you can add this type of symbol, and then you can replace this A with B. Now these things are allowed. So this is how you can do your transformation into CNF. Let's assume you have this type of production. A goes to AAB. This is not allowed. You know, this is not allowed. So what you will do, you will do this. You will do this. For this terminal, you make a new symbol. You can make a new symbol like D goes to A. You can make. This is allowed. Now what you can do, you can replace this a with d. But remember, this is also not allowed. Three variables are not allowed. So what you can do, you can take two variables. For example, this ab, you can take this ab, you can make a new production like this, c goes to ab. So now you can replace them with c. So now you got your cnf. So this is very simple transformation into cnf. So basically what you will do, very simple. For every terminal you just define a new symbol. E1 goes to A, E2 goes to B. For every terminal symbol you are defining new variables. Now for the remaining, what you can do, you can basically you can any like you can do like this. E3 goes to some E4, E5 and so on. So this type of productions you can make. For example, we can take an example. Let's take this. S goes to A slash double A. A goes to AB slash A, and B goes to small b. Let's assume you have this. You want to convert this into CNF. Then what you can do? Very easy, very easy. Just directly make for each terminal, just directly make some symbols, specific symbols. For example, you can for each symbol. So what you can do? You can make like this. E1 goes to A, E2 goes to B. This is how you can make. So directly write it. Now E1 goes to A, E2 goes to B. So now this A basically can be replaced with E1. Okay, these two A's can be replaced with E1, E2. Sorry, E1, E1. Okay, E1, E1. Okay, this A can be replaced with E1. This B can be replaced with E2. So now what you do, you can see this thing is not allowed. So you what you do for this thing is not allowed. So what you can do for this AB, you can define some new symbol, maybe some symbol C you can define for AB. Now this AB you can replace with C. Now everything is, oh, no, this still is not fine, because one variable is not fine. One variable is not fine. So okay, when you have one variable, then actually just let it as it is. This even, okay, don't change it, because one variable is not allowed. So don't change it. Okay, leave it as it is. So this is your CNF. Okay, this is like just a small like manipulation. Okay, what are the productions that you are allowed, you are just making use of those productions, and whichever production is not allowed, you are somehow trying to change it. Okay, so like it is just like this is how you can do. Okay, this is how you can transform into CNF. Let's take this example. Let's consider this example. This is your original grammar. S goes to ASA, AB, A goes to and so on. These are the things that you have. So first you will remove the null production. This is your first thing that you need to do. You want to remove the null production. Now in this one example, we will see everything. In this one example, we will see how to remove null production, how to remove unit production, how to remove useless symbols, and then how to convert into CNF. Everything we will see in this one example. So this is your original grammar. You want to remove null production. So what you will do? First, you will find all the nullable symbols. What are the nullable symbols? This B is directly nullable. You can see this B is directly nullable. Because this B is nullable, so because of this B is nullable, so A is also nullable. Now A and B both are nullable. A and B both are nullable. Now nothing else is nullable. You can see nothing else is nullable. So A and B are nullable. A and B are nullable. What you will do? First, you will write this. Just directly write a new start symbol, because in the procedure of eliminating the null production, what we do? We make a new start symbol. So S0 goes to S. This new start symbol you are adding. Just directly add it. Okay. Now, after adding this, what you can do? So you have directly added. Now what you do, because this this A and B are nullable, so here this A and this A, these are nullable. So what you will do, you will remove the first, you will leave it as it is. You will leave it as it is. Okay. Okay, yeah, actually in this he is going step by step. Actually in these slides he is going step by step. So the first thing he has done is just he has added this thing, nothing else he has done. Okay, just added these thing. Now in the next step, he's basically doing this. These A and A are nullable symbols, so you leave it as it is. You remove the first A, you remove the second A, you remove both of the A's. This B is nullable, so you leave it as it is. You remove the B. This this B is nullable, so you leave it as it is and you remove it. But if you remove it, then you will get epsilon, so you don't want to get epsilon, so don't write that epsilon, because you want to remove the epsilon production. This s is not nullable, so leave it as it is, and this epsilon you can remove. This is how actually you will get your removal of null production. This is how you will get, you can just check it out. So this is how you will get finally. Okay, here also finally what you will basic, this is the final grammar that you will get. Wait a second. This is the final grammar that you will get after removal of null production. This is the final grammar that you will get. You can just check it out. So this is the final grammar you have gotten after null productions. Now once you have done the null production, now what you can do, you can try to remove the unit production. I told you, once you have removed the null production, now you can try to remove the unit production. How to remove unit production, this I already told you. First of all, just find out what are the unit production. S0 goes to S, this is a unit production. This S goes to S, you can directly remove. Actually this S go, this type of unit production you can just directly remove. S goes to S. Okay, without worry, you can directly remove. So this S goes to S, you can directly remove. Nothing you need to do. This you can directly remove. Okay, remember, S goes to S, A goes to A. This type of production you can directly remove. So you can remove this directly. Now S0 can go to S. Now this S can go to something like no. You can see. So this is the null unit production that you have. S0 goes to S. And what is the other unit production you have? A goes to B, this is also unit production, and A goes to S, this is also unit production. So these are the unit productions you have. So these are the unit productions you have. What you can do, very easily you can apply the unit production removal algorithm. So what you will do, when you remove this unit production, then what you will do, put everything that is, see this S is, you are removing this S, this unit production you are removing, so put everything here, remove this and put everything here. So what you will get, you will get S0 goes to everything. You can see, of course, this S you directly remove, so you don't have to write it. This S you don't have to write anyway, because this S you can directly remove. S goes to S, this you can directly remove anyway. So now when you remove this A goes to B, then what you need to do, just write everything here. So this B you write in place. Similarly, when you remove this S, then write everything here. So finally what you will get, so finally you will get this. So okay, you can say this S, okay, is not there, you can say. Anyway, this is the final grammar that you will get after removal of unit production. You can go through these slides, everything is there, step by step he has given, step by step. This I have taken from the book Sipser. So there is a theory of computation book, Sipser. From this book, I have taken this example. He has given everything in a very detailed manner. You can see step by step. So you can go through these slides, but you already know how to remove null production, how to remove unit production. And now we will remove the useless symbols. Let's see if there is any useless symbols here. So this anyway. So this is not. Let's see if there is any non-generating symbol do we have. So you can see everything is generating symbol. Now is there any symbol that is not reachable? So you can see everything is reachable. S is reachable, A is reachable, B is reachable. So everything is reachable, everything is reachable, and there is no symbol which is not generating. So there is no useless symbol here. You can see there is no useless symbol. So finally you have removed null production, you have removed unit production, and there is no useless symbol, so there is no need to remove useless symbols. But anyway, now you can convert this grammar into Chomsky normal form. How will you convert? Very easily. See, this is okay, but this is not allowed. Okay, see, so what you can do, for every terminal you can make a new variable. This is how you can make. For every terminal you can make a new variable. You can see u goes to A, B goes to B. For every terminal you can make a new uh, new variable, and this is just some manipulation. For example, you can see here this a as a is not allowed. So what you can do, if this is not allowed, so what you can do, you can, yeah, what you can do, for this assay you can make something new. This assay, for this assay you can make a new variable a1. Now this assay you can remove and you can put a1. So this is how you can do some manipulation, just some manipulation. So from this grammar you can get this Chomsky normal form. Okay, you can see everything is in Chomsky normal form, you can see, because in Chomsky normal form we allow this type of production. This type of production are allowed, and two variables, you can see everywhere you will see either two variable or one terminal, either two variable or one terminal, either two variable or one terminal. So this is your Chomsky normal form. So any doubt in this Chomsky normal form, anyone? Any doubt in epsilon, null production removal, unit production removal, useless symbol removal, and Chomsky normal form? In these three things, do you have any doubt? Aditi, Gayatri, Harshita, any doubt? Okay, so you can try questions and you can do some practice. So anyway, in the gate exam they will give you options, so you don't have to worry, because in gate exam if they ask you to convert something into Chomsky normal form, then there will be options also A, B, C, D. So very easily, easily you can do these things. But anyway, this is how you can do all these four things: simplification of grammar and conversion into Chomsky normal form. Now we will see something called Grabeck normal form. This Grabeck normal form, we will just see the definition. We won't see how to convert into Grabeck normal form. That is not required. That is a actually quite hard. That is, so we won't do that. Okay, we will just see the definition of Grabeck normal form. This is Grabeck normal form. As I told you, every grammar can be converted into CNF. Similarly, every grammar can be converted into GNF form. This is called Grabeck normal form, means GNF form. So every grammar can be converted into GNF form also. In this form, we only allow one type of production. This is the only production that is allowed. What is the production? A variable is going to terminal followed by sequence of variables. Followed by sequence of variables. So all variables, sequence of variables. So this is the only type of production we allow. So basically x goes to a beta. A is a terminal symbol, and this beta is a sequence of variables. So this is your Grabeck normal form. So in the Grabeck normal form, we only allow one type of production. And what is that production? That production is basically variable goes to terminal followed by variable. For example, this is allowed, because you can see here there is no variable that is allowed. Okay, a goes to a, this is allowed, because you can see here you can say that variable is going to terminal followed by a sequence of variable. There is no sequence here, so this is allowed. A goes to a, this is also allowed. A goes to ab, this is not allowed. This is not allowed in GNF. This is not allowed. A goes to a b, this is also not allowed. Okay, a goes to a b, a, this is also not allowed. So you can see what is allowed, you know. For example, a goes to a b c d, this is allowed. So basically what is allowed? A variable goes to terminal and followed by sequence of variables. I can write v star. V star means sequence of variables. So this type of production is this is the only production that is allowed in Grabeck normal form, GNF. Okay, so this is the definition of. We will not see how to convert into GNF. That is not required, absolutely not required, and that is not easy also. They are not going to ask you in the GATE exam. So just the definition we have seen. Even in the GATE exam so far, they have not asked the definition also. The GNF is completely untouched. They have not asked any single question from the GNF. So okay, everything else we have already seen so far. So let's take a 10 minutes break, and after the break we will study something called closure properties. After the break we will study closure properties of regular languages and CFLs. We will study these properties, closure properties. Okay, so take a 10 minutes of break. We will start at 6:45. Okay. So now we will study something called closure property. What is closure property? So in the group theory, if you remember, in the group theory we have already studied something called closure property. In the group theory, what was closure property? You have a base set. This is your base set. So this is your base set S, and you have some operation. Let's assume this star is the operation. So what you do? This is your base set. Base set. So from this base set, what you do? On the elements of this base set, you apply the operation. This star operation you apply. For example, A star B. So you take two elements A, B, and you apply the star operation. Then the closure property says that the result should also go in the base set. The result also should belong to the base set. This is closure property. We will say that this set S is closed under star operation. This is what we say. So in the group theory, we have already seen this closure property. Anyone has any doubt in this closure property? I hope you remember in the group theory we have already seen many examples. For example, you have set of integers. This is your base set of integers. This is your base set of integers, and addition operation. You know that this set of integers is closed under addition operation, because if you take any two integers, any two elements you take from this set, on those elements if you apply this addition operation, then the result will also belong to this set. So that's why this addition operation on set of integers is closed, or you can say set of integers is closed under addition operation. Set of integers is also closed under subtraction operation. If you take any two integers and you apply the subtraction operation, then again the result will also belong to this set of integers. So you can say set of integers, this base set of integers is closed under subtraction operation. For example, set of natural numbers, this is closed under addition operation. Set of natural numbers is closed under addition operation. This is our base set. In this base set we have all the natural numbers. So set of natural numbers is closed under addition operation. Okay, because if you take any two natural number and you apply this operation, then the result will also be a natural number. So the result will also belong to this base set. Set of natural numbers, can you tell me this set of natural number is closed under this subtraction operation? Can you tell me this set of natural number, it is closed under the subtraction operation? Can you tell me is this true or false? So you can see this is false, because it is not closed. Set of natural numbers is not closed under subtraction operation, because if you apply, for example, if you apply 3 minus 4, then the result is -1, and this result does not belong to our base set. So this is our closure property. Now we have some closure properties of regular languages. First we will see closure properties of regular languages. What are the closure properties of regular languages? So your base set is set of regular languages. Remember, your base set is set of regular languages. Set of regular languages. You can say this is your base set of regular languages. Some students make this mistake. This is a mistake that some students make. Remember, this is set of regular languages. Every regular language is here. This is not a particular regular language. For example, this sigma star is a particular regular language. This is a particular regular language. This is a regular language. But this is set of regular languages. So here you have sigma star, here you have phi, Here you have even number of A's, even number of B's, all the things that we have seen in when we were discussing NFA, DFA. At that time, we have seen many regular languages. Regular language is a language which is accepted by some DFA or some NFA. So anyway, this is set of regular languages. Remember, so we will call it regular set. We will call it regular set. So regular set means set of regular languages. This is our base set. Okay. Now on this base set of regular languages, on this base set, if you apply the union operation, means you take two regular languages, you apply their union, basically union of two regular languages. Okay. You have regular language L1, you have regular language L1, and you have regular language L2. Regular language L1, L2. Then their union will also be regular. This we have already seen, if you remember. This result we have already seen, because very easily you can prove it. Because this L1 is regular, so this L1 has a regular expression. This L1 is regular, so it has a regular expression. This L2 is regular, so it has a regular expression. So what is L1 union L2? L1 union L2 is nothing but language of R1 plus R2. And this is a regular expression. R1 plus R2 is a regular expression. Okay, so if this is a regular expression, this is a regular expression, then we have seen that R1 plus R2 is also regular expression. Because this R1 plus R2 is a regular expression, so the language of this regular expression will be regular language. So you can see that union of two regular languages is regular. So what are the properties? All these properties we have seen so far. So union of two regular languages is regular. Okay, so means basically closed. The set of regular languages is closed under union operation. If I give you set of regular languages, that is your base set. From that base set, if you take two elements, basically you are taking two regular languages and you apply union, then the result will also be regular language. So the result will also belong to the base set, because because the result will also be regular. So you can see regular languages are closed under union. Regular languages are closed under complement. This also we have seen, and we have also seen how to make DFA for the complement language. If you remember, I told you that just exchange the set of final state and set of non-final state. Just do the exchange. Okay. So we have already seen that set of regular languages are closed under complementation operation. Okay. Now these two things are true. So you know what is A intersection B. If you have two set A and B, then what is A intersection B? A intersection B is nothing but A complement union B complement whole complement. This is a property. So very easily you can prove this property. A intersection B, this is a very nice property. Okay, you should remember this also. In the set theory, using the Venn diagram, you can prove this very easily. Okay, A intersection B is nothing but A complement union B complement and whole complement. This is your A intersection B. So you know that if you have A is regular language, let's assume A and B are regular languages, both are regular languages, then A complement is also regular language, B complement is also regular language, and regular language union regular language is also regular language. So this complete thing is also regular language, and the complement of regular language is regular language. So this finally this complete thing is regular language. So what you can say, A intersection B is also regular language. So you can say that regular languages are closed under intersection also. So we have seen regular languages are closed under union, regular languages are closed under complementation, regular languages are closed under intersection. Now let's talk about this reversal. Regular languages are closed under reversal also. This also we have seen, if you remember, how to make this, how to make a reversal. So this also we have seen. For example, I told you at that time, this language reversal we have seen, right? Regular language reversal, how to make a NFA for the reversal of a language. If you have an NFA for language L, then how can you make NFA for L reverse? This is we have seen, right? Anyone? Let me know. how to make NFA for reversal of a language. Yeah, I think this we have seen, because what we do, if you remember what we do, so we just have one final state we have, and that final state we make initial state and we reverse all the arrows. So this was reversal, if you remember. I think we have already seen this, so you can refer to the previous lectures if you don't remember. Okay, so we have already seen that if you have NFA for L, let's assume this is NFA, this is NFA N1 for L, then from this NFA you can make NFA for and NFA N2 you can make for LR, reversal of language. This we have already seen. If you don't remember, then you can just watch the previous recordings. This is already covered. Okay, so you can see that regular languages are closed under reversal operation also we have seen that if two languages are regular, then their concatenation is also regular. This also we have seen. I told you have this is your NFA for L1, this is your NFA for L2. Then what you do, you make a new initial state and you make epsilon move. So this is this construction also we have seen. So this construction, okay, in the previous lectures we have already seen this construction. So this was the proof. So this proof we have already seen that if L1 is regular, L2 is regular, then concatenation L1 dot L2 is also regular. So this also we have seen. So regular languages are closed under concatenation operation, and we have seen that regular languages are closed under this clean star. We have already seen how to make NFA for clean star. So L plus, if L is regular, then L plus is also regular. This also we have seen. All these things we have seen so far. Everything we have seen so far. Now, so what you can say these things. You can say that if L1 and L2 are regular languages, basically regular language, set of regular languages, they are closed under union, yes. They are closed under intersection, yes. They are closed under complementation, L bar. Complementation, yes. They are closed under reversal, yes. They are closed under concatenation, L1 dot L2, yes. They are closed under clean star, yes. They are closed under clean plus, yes. So you can see regular languages are closed under all these operations. Now, for example, if I give you L1 minus L2, L1 is regular, L2 is regular, and in the exam they ask you L1 minus L2, L1 minus L2. What is this minus? This is set difference. We have already seen what is set difference in the set theory. When we were discussing this discrete mathematics, there we have already seen what is set difference. Now my question to you is, so this type of question they can ask you. Question is, L1 is regular, L2 is regular, then can you say L1 minus L2 will be regular or not? Yes or no? Can you say that L1 minus L2 will definitely be regular? Can you say this? Yes or no? Tell me. Anyone else? Aditi, Gayatri, Harshita? Can we say that L1 minus L2 will be regular? Can we say this? Can you give me reason? Like, Sanjeev, can you give reason why you are saying that L1 minus L2 will be regular? How can you say, like, how can you prove it that L1 minus L2 will be regular? Okay, let me give you the reason. So this L1 minus L2 is basically, you can write like this. In the set theory, we have already seen these things. A minus B. This is set A, set B. What is A minus B? So this is your set A, this is your set B. So this is your set A, this is your set B. What is A minus B? A minus B is this area. This area is A minus B. This A minus B can be write like this: A intersection B complement. This, like this also you can write: A intersection B complement. So this A minus B, this A minus B, this is nothing but A intersection B complement. Now let's assume A is regular language, B is regular language. So A is regular language, B is regular language, and we have seen that B complement will also be regular language. This we have seen, that this B complement will also be regular language. So this is regular language, this is regular language, and we have seen that regular languages are closed under union. So this complete thing will also be regular language. See, regular languages are closed under complementation, and regular languages are closed under intersection. These things we have seen. So B complement will also be regular. A is already regular. Regular intersection regular, that will be regular. So the complete thing is regular. So you can say A minus B will also be regular. This is how you can prove. In exam, they can give you anything like A XOR B. Let's assume A is regular, B is regular. Let's assume A is regular, B is regular. Then they can ask you, can you say that A XOR B will be regular or not? Try this. Can you say that A XOR B will be regular or not? Yes or no? Right. So actually, what is A XOR B? What is this A XOR B? This A XOR B is this. This is symmetric difference. Remember, this we have already seen. Symmetric difference means A minus B union B minus A. A minus B union B minus A. In the set theory, this we have already seen. Okay. This A minus B actually is nothing but A intersection B dash. So I can write A B dash intersection. This is intersection A intersection B dash plus union. Union I can write plus B intersection A dash. Both are same. Anyway, this is our symmetric difference, if you remember. In the set theory, we have already seen. So if A is regular, B is regular, both are regular. We have already seen that this A minus B will be regular. We have already seen that this set difference. Regular languages are closed under set difference. This we have already seen. So this A minus B will be regular. B minus A is also regular. Regular union regular is also regular. So you can see that this A XOR B, this is also regular. So this is how they can ask you questions. Okay. You know these results. Now, actually, regular languages are closed under most of the operations. Okay. Whichever random operation they can give you, any random operation they can give you. Regular languages, set of regular languages, they are closed under most of the operations. Most of the operations. There are some operations under which they are not closed. So actually, most of the operations they are closed. Whatever you put, set difference, symmetric difference. Okay, like you put any random operation, maybe you put your own operation, and you will see most of the operation. Most probably, this regular languages are closed under almost all the operations. Okay, what are the operations under which regular languages are not closed? So let's see those operations under which regular languages are not closed. What are those operations? So these are the famous operations. The first is infinite union. This is infinite union. Okay. So infinite union means you have infinite union of regular languages, like okay, L1 union L2 union L3 and so on, infinite union. So this infinite union is not closed. See, finite union is closed. L1 union L2 is closed. L1 union L2 in union L3, this is also regular. If L1 L2 L3, if these three languages are regular, then their union L1 union L2 union L3, this is also regular. You can do any finite union. You can do any finite union. You will see that they are closed. Okay. But infinite union, when you do infinite union, infinite regular languages, this is regular, regular, regular. But this is infinite union, then this is not closed. How can you prove it? Very easily we can prove it. You already know that A power n, B power n is not regular. This we already have seen. because here what we need to do, here we need to do the unlimited counting, unlimited comparison. A power n, we need to count how many a are there, we need to count how many b are there, and we need to match number of a equal to number of b. So this is an unlimited comparison we have. N, this is unlimited comparison we have. So this a power n b power n is not regular, this we have already seen. But this a power n b power n, you can write it as an infinite union of regular languages very easily. How can write? Epsilon union ab union a square b square union a cube b cube, and so on. You can see that this epsilon, this is regular, ab, this is regular, because every finite language is regular. So this is a finite language, this is a finite language, this is a finite language, this is regular, this is regular, every language is regular, and you are taking their infinite union. So you can see when you take the infinite union, then the result is non-regular. So the result is a non-regular. So what you can say, that regular languages are not closed under union operation. Okay, is it clear? Anyone has any doubt in this? Basically, you are having regular languages. This is regular, 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 regular. You are having infinite number of regular languages. You are doing their infinite union. Then the result may not be regular. You can see here the result is not regular. So result may not be regular. So that's why we can say that regular languages are not closed under infinite union operation. Infinite union. Okay. And from here you can easily see that they are not closed under infinite union, so they are not closed under infinite intersection also, because intersection can be written in union form. For example, L1 union L2 union and so on. This infinite, this is infinite union. You can write it like this: L1 intersection, sorry, L1 bar, L2 bar, and so on, complete bar. So you can see that this union, this infinite union, can be written like this. Okay, so you can prove that regular languages are not closed under infinite intersection also. Why? Because if they are closed under infinite intersection, then they will be closed under infinite union. We have already seen that regular languages are not closed under infinite union. We have already seen this. Regular languages are not closed under infinite union. Now we can say that regular languages are not closed under infinite intersection also. How can I prove it? Very easily. Very easily. Assume that they are closed under infinite intersection. Assume that they are closed under infinite intersection. Then they will be closed under infinite union also. Why? Let's assume L1, L2, L3, everything is regular, 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 regular. Then you know regular language complement is regular. So this is regular, and so on. Now we have assumed that infinite intersection is regular. So this complete thing will be regular. We already know that regular complement is regular. So you can see that infinite union will also be regular. So what we have shown? We have shown that if we assume that regular languages are closed under infinite intersection, if we take this assumption, then automatically we will also prove that regular languages are closed under infinite union. But this is not true. This is not true. We have already seen that in regular languages are not closed under infinite union. This we have already seen. So that's why what we can say, that our assumption was incorrect. Our assumption was wrong. So what we can say, that regular languages are not closed under infinite intersection. Regular languages are not closed under infinite union. Okay. So now the next thing. So basically regular languages are not closed under infinite intersection, infinite union. The next operation under which regular languages are not closed, that is subset operation. Subset operation. What is subset operation? Assume I give you a regular language. This is regular language. This is a regular language. Now I give you a subset of L. Can you say Can you say that L will be regular? Can you guarantee that L will be regular? Yes or no? Anyone want to try this? Before I explain, anyone want to try this? Tell me why. Can you give me? Can you tell me why you are saying that no? Okay, let's see here. See, I told you L is regular language. L is regular language. Assume that A is subset of L. Now, can we say that A will be regular? No. Very easily we can prove. Assume that L is sigma star. We know sigma star is regular. This we know. Sigma star is regular. Sigma star is regular, and we also know that every language is subset of sigma star. Every language is a subset of sigma star, and the sigma star is regular. So even this language, A power n, B power n, even this language is also subset of sigma star. This language, A power n, B power n, this language is also subset of sigma star. So basically the sigma star is regular. This language is subset of regular language, but this language is not regular. So you cannot guarantee that A will be regular. So what you can say? You can say that, you can say that, what you can say? You can say that regular languages are not closed under subset operation. Okay, regular languages are not closed under subset operation. This is what you can say. So anyone has any doubt in this? So regular languages are not closed under subset operation. Similarly, you can show that regular languages are not closed under superset operation. Very easily you can prove. Why? Basically, if I tell you L is a regular language, and let's assume A is superset of L. Let's assume A is superset of L. Then can you say that A will be regular? Can you say that A will be regular? Try this. Yes or no? Anyone want to try? Okay, let's see. See, L is regular. Okay, and we are saying that let's assume A is superset of L. Then can we say that A is regular? No, we cannot say. Why? Take this language. L equal to 5. You so you see that this is empty language. Every finite language is a regular language. This empty language is also regular language. So this L is regular. This phi is regular. So this phi is regular, and you know that this A power n, B power n is superset of phi, because actually phi is subset of everything. Phi is a subset of every language. So A power n, B power n is what? This language, A power n, B power n, this language where n is greater than equal to 0, this language is superset of phi. Okay, this language is superset of phi, empty set. But this language is not regular. So what you can say? You can say that regular languages are not closed under superset operation. Anyone has any doubt in this? Anyone? So this is how you can prove that regular languages are not closed under infinite union, infinite union, infinite intersection, subset, and superset. These are the famous operations under which regular languages are not closed. Most of the other operations like union, intersection, complement, set difference, okay, complement, reversal, star, plus, set difference, okay, most of the operations regular languages are closed. So these four were the famous operations under which regular languages are not closed. Okay. Anyone has any doubts so far? So these were the closure properties of regular languages. Now we will see closure properties of CFL languages and closure property of DCFL languages. But before we go to that, anyone has any doubt so far? These closure properties are very important. Any doubt? Anyone? Okay, then let's start closure properties of CFL languages. CFL languages. CFLs are actually closed under union. These are closed under intersection. These are not closed under intersection. These are closed under. These are not closed under complementation. These are closed under all other, like concatenation. These are closed. Concatenation. These are closed. So these are the famous operations under which they are not closed. Let's see one by one. We will see. First, let's see union. Union of two CFL is always CFL. How can you prove it? Very easily. Let's assume L1 is CFL, L2 is CFL. Let's assume L1 is CFL, L2 is CFL. So L1 has a PDA. Let's assume this is PDA for L1. Let's call it P1. Let's assume this is PDA for L2. Then you can make PDA for L1 union L2. How? Very easily. Just make epsilon transition here and here. Epsilon, 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 epsilon. This is how you can make. So you can see now you can oh sorry, this is just initial state. This is initial state. Basically make a initial state and put epsilon transitions to P1 and P2. This is PDA for L1, this is PDA for L2. So now this is how you can accept L1 union L2, because now this complete thing is a PDF for L1 union L2. This complete thing is a PDF for L1 union L2. So this is how you can show that these CFLs are closed under union operations. Now let's see intersection. CFLs are not closed under intersection, and to see that we will take one famous example: a power n, b power n, c power n greater than equal to 0. Here this language is actually not CFL. Let's see why. See what you will do if you want. Let's assume this language I give you, and you want to accept this language using your PDA. So what you will do? You need this comparison. A should be equal, number of A should be equal to number of B. Number of B should be equal to number of C. These two comparisons you need. This comparison, this comparison. These two comparisons you need. So what you will do? You will do like this. I give you this A, B, B, C, C. Then what you will do? You want to compare number of A equal to number of B. So what you will do? You will read this, you will push it. You will read this, you will push it. When you read this B, then you will pop it. When you read this B, then you will pop it. Okay. Now when you go to C, so okay, this A power n, B power n, this you have checked. This comparison you have done. This comparison you have done. But now when you read this symbol C, there is no A or B left. You can see. Now there is nothing to compare, because all the A's you have already consumed, all the B's you have consumed with A's. So when you go to C, then nothing is left for C. You can't compare. You can't find out that number of C will be number of C will be equal to number of A or B. So this you can't find out. So you can see we can't accept this language by PDA. Is this point clear? Anyone has any doubt in this? Because you need two comparisons here. You can see. So once you are done with this first comparison, now you don't have the information of how many A's were there. You don't have information how many B's were there. So you have nothing to compare with the number of C's. Okay, is this point clear? Anyone has any doubt in this? If anyone has any doubt, then you can ask. See, we have already seen this WWR. This is CFL. This we have already seen. We have constructed PDA also. This WWR we have constructed PDA also. This WWR is why this is CFL, let me tell you. Because the WWR is saying like this. Let's assume you have this string AB. Then this is W. Then what is WR? That WR is this. This is CFL why? This is CFL because in stack what you will do, you will push it A, B. Now basically you need to compare this with this, and on top you have this. So you can compare. You need to compare this with this. So when you see this symbol, then you can compare. So basically you are doing the reverse comparison. You can see what I'm saying. I'm saying this. You are doing reverse comparison. So you pushed this AB. You have pushed it on the stack AB. Now on top of the stack, what you have? You have B. And when you have W reverse, what is W reverse? This is W reverse. When you have W reverse, then you need to compare this B with this B. This is what you need to compare in the WWR. In the WWR, this is what you need to compare. You need to compare this with this. So that's why on the top you already have this B, so you can compare. Similarly, you can compare and so on. This is how you can do. Okay, this is how you can do. But now consider this language WW. What is the meaning of this WW? This is the meaning. AB. Let's assume this is W. Let's assume this is the first half. This is the first half W. Then you have again W, means AB. Now this type of this language, WW language, you cannot accept using PDA. Why can't you accept? Very easily you can see. What you will do when you see this W, see, you need to compare this W with this W. You need to do this comparison. So you need to remember what is this W. You need to remember it. Where will you remember it? You will remember it in the stack. So you will push it on the stack. This AB. Because you need to remember it. Because you need to compare this first half with the second half. Okay, this first half must be equal to second half. But now once you go to the second half, there is a problem. What is that problem? This A actually should be compared with this A, because this is WW. This is not WWR. This is WW. So actually this A should be compared with this A. But on top of the stack we have B. On top of the stack we do not have this. And this stack has this property. This stack has this the stack data structure has this property that you can only see the top of the stack. You can only see this. You cannot see this. You cannot see this. You can only see this. So you cannot compare this because you want to compare this A with this A. So basically when you see this next A, you want to see whether this bottom symbol is A or not. But now you don't know whether the bottom symbol is A or not. You don't know. Because you can only see this symbol. You can't see this symbol. So that's why this WW cannot be accepted by stack, or this WW language cannot be accepted by PD. Is this point clear? WWR we can accept because we are doing the reverse comparison. The stack can do this, but WW means forward comparison. You are pushing it and you are comparing this with this. So basically this is forward comparison. So this forward comparison you cannot do with PDA. Is this point clear? Anyone has any doubt in this point? Now, okay. So let's see some examples and let's try to see whether those languages are regular CFL and so on. Also, before we go, let's see some examples where the language is not DCFL. For example, this is a DCFL because the push and pop are clear. You need to push every A, and with every A you need to pop one B. So push and pop are clear. This is DCFL. You can make DPDA for this. We have already seen this. You can make DPDA. We have already constructed DPDA for this language. A power and B power 2n. This is also DCFL. Why? Because it is clear how much to push, what to push, how much to push. Everything is clear. Because when you see this A, then what you do? You push two A's. For every single A, you push two A's. For every single A, you push two A's. Okay. So you can see that A power and B power 2n, push and pop are very clear. Okay. For every A, you push two A's, and for every B, you pop one A. For example, A, B, 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 B. For example, this. So when you see this A, then you push two A's. When you see this A, then you push two A's. When you see this B, then pop one A. When you see this B, pop one A. When you see this B, pop one A. This is how you can do. Push and pop are very clear. Now let's see this. A power n, B power n, union A power n, B power 2n. This is not DCFL. This is not DCFL. Why this is not DCFL? Because push and pop are not clear. Let's assume I give you some string. You don't know what to do, how much to push. For example, if I give you some string, I give you. This is the string I have given you. Now you don't know whether this string belongs to this part or whether this string belongs to this part. If this string belongs to this part, then what you need to do? You need to push one A for each A. Okay. If this string belongs to this part, then what you need to do? You need to push two A's for each A. So the push and pop are not clear. DCFL means deterministic. So everything should be clear. Everything should be clear. Like what you do, what you want to do next, that should be clear. You don't have any choice. This is deterministic. So you can see here push and pop are not clear. Basically, you don't know whether to whether your string belongs to this part or whether your string belongs to this part. This you don't know. Okay, and because you don't know that, so what you can say? You can say that this is not DCFL because DPDA cannot do it. We need non-determinism. If you want to do it, then you need non-determinism. Just give me 2 minutes. Just give me 2 minutes. Some work. Sorry, some work came up. Yeah, what I was saying that this is not DCFL. Okay, because the push and pop is not clear. Basically, in the beginning, you don't know what to do. In the beginning, whether to push one A for each A or whether to push two A for A, that is not clear. So you need non-determinism here. So that's why this is not a DCFL. So for example, you can now let's take some examples and we will try to see whether these languages are regular, DCFL, CFL. These things we need to see. Let's take some examples. So first example, 5. Tell me all these things. Is this regular? Yes or no? Now back to back question answer will be going on. So just keep your hands on the chat box. Tell me, is this regular? Yes or no? Regular. 5. 5 means empty set. Is this regular? This is regular. Okay, so in this, basically here I will write whether this is regular or not. Is this DCFL? Tell me, is this DCFL? So for this language, just tell what are these, like R, D, C. write like this. If this is R, then you can write R. If this is D, then so you can write like this, RDC. If this is both all three, then you can write RDC. So tell me. So this is regular. Every finite language is regular. This is empty set. This is empty set. Every finite language is regular. So this is a finite language. So this is regular. And we have already constructed the DFA for this. We have already constructed NFA for this. If you remember in the beginning of the lectures, when we were studying DFA NFA, at that time we have already constructed DFA NFA for this language phi sigma star. For many languages, around 15-20 languages, we constructed DFA. So this is a regular language. Every finite language is a regular language. This is a finite language, so this is regular. Every regular language is DCFL. Every DCFL is CFL. Okay. So this empty set is a both regular DCFL CFL. What about this? This language. What about this language? Tell me RDC. What it is? What it is not? Tell me. This again is a finite language. This is a finite language. Every finite language is regular. Every regular language is DCFL. Every DCFL is CFL. Okay. Try this question. So every finite language, basically any finite language, every finite language is regular. Every regular language is DCFL. Every DCFL is CFL. Okay. Let's see. A power n, B power n plus 2. Tell me RDC. Tell me RDC. Tell me what it is. This is not regular. This is DCFL and this is a CFL. See, first of all, this is not regular. Why? Because unlimited counting is there. A power n plus 2. You need to count number of A's and you need to match them with number of B's. So basically, number of B's should be 2 more than number of A's. For example, if your number of A's are 3, then number of B's should be 5. Number of B's should be 2 more than number of A's. So there is a comparison here. And because you have this unlimited comparison, so this is not regular. This is DCFL because the push and pop are very clear. The push and pop are very clear in this. Okay, what do you need to do? Push every A. For example, if you have, okay, what do you do? How will you make DPDF for this? Very easily you can make. You push every A. So you push every A. Then what you do? Don't basically your DPDF, what it will do? 2 B's it will just take extra, and the remaining B it will try to match. So match. Once it sees a Z0, then he will try to see whether 2 B's are there or not. So basically, after encountering this B0, after encountering this Z0, it will just try to see whether 2 B's are there, and then it will go to final state. What I'm saying like this. This A power n, B power n plus 2, A power n, B power n plus 2. This is nothing but A power n, B power n, B power 2. So what you need to do? You need to match this A power n, B power n. You need to match this. Once you have matched this, basically, once you have done A power n, B power n, then what will happen? Then your stake will have Z0. Once you have done this A power n, B power n, then your stake will have Z0. Once you see this Z0, then you just try to see whether after this Z0 you take 2 B's. Then you will go to final state. So push and pop is very clear. So this is DCFL. Every DCFL is CFL. Now let's see this A power n, B power m. M is greater than equal to n. Tell me about this. RDC. Tell me about this RDC. Okay, let's see. This is not regular because here again you need comparison. Number of B should be greater than equal to number of A. So you need unlimited comparison here. Number of B should be greater than equal to number of A's. So unlimited comparison you need here. So this is not regular. This is not regular. This is a DCFL. This is DCFL. Why? Because push and pop is very clear. What you need to do, you just push every A. Okay, you push every A, and then you try to match A's with B's. And then when you see this Z0, then you can have any number of B's. So basically, it's like this. It's like this. These are number of A's, A power n. These are B's, A, B power n. And then you can have anything, B star. B star. What is this? This is nothing but A power n, B power m, where m is greater than equal to 0. This language, A power n, B power m, where m is greater than equal to 0, this language you can write like this. A power n, B power n, then B star. Basically, any number of B's you can have here. This is DCFL. Why? Because the push and pop is very clear. Number of A's should be matched with number of B's. Once you have done this matching, then you can have anything B star. You don't have to worry. Then you can have anything B star. Basically, you can have any number of B's you can have. So this is DCFL because DPDA can do this. Anyone has any doubt in this? In these things, anyone has any doubt? Like you are not answering, so that's why I'm asking. If you have any doubt, then you can ask. Aditi, Gayatri, Harsita. Okay, let's take more examples and maybe it will be clear by taking more examples. This language we have seen, WWR. This language we have seen that this language is not regular because you need to do comparison. You need to compare the first half with the reverse of the second half. This is not DCFL because this we have already seen that this is not DCFL because you don't know where this half will come. You don't know where this half will come. So this push and pop is not clear. You don't know when to start popping. When to start popping, that is not clear. Okay, when to start this pop, this is not clear. The pop should start at the half, but you can't know the half. How to know this half? You don't know. So this is not DCFL because you don't know when to pop, when to stop pushing, and when to start popping. This is CFL. We have already constructed the PDF for this. WWR. W hash WR hash or C. For example, yesterday we have already seen WCWR, where W belongs to AB star. Where W belongs to AB star. Okay. So this WCWR, this WWR, the W hash WR. This is not regular because you need to do the comparison here. You need to compare this W with this WR. You need to do this matching. You need to match this W with this WR. So this is not regular. This is not regular. But this is DCFL. This is DCFL. Why? Because now you know where the middle will come. The middle will come when you see the hash symbol. Then you know this hash symbol will tell you the middle has come. Similarly here, the symbol C will tell you that the middle has come. So now the push and pop is very clear. Like you will push everything before this before you see this C. After this C, you will pop everything. So you will push everything. Then you will see this symbol C. This symbol C will tell you that the middle has come. The middle has come. Now you will pop everything. So the push and pop is clear. So this language is not regular, but this language is DCFL and every DCFL is CFL. So this is CFL also. Okay. This WW. Let's assume W belongs to AB star. This WW we have already seen. This is a not CFL. This is not CFL, so this is not regular. This is not regular because here you need to do the matching. The first half you need to match with the second half. So this is not regular. This is not a CFL because I told you why this is not CFL. We have already seen why this is not CFL because PDA cannot do this. The stack cannot do this. Stack cannot do the forward matching. So the stack cannot do this. So this is not CFL. This is not CFL. And because this is not CFL, so this is not DCFL also. Because every DCFL is CFL. So you can say if this is not CFL, then this is not DCFL. So this is neither DCFL, this is neither CFL, this is neither regular. A power n, B power n, C power n. We have already seen that this language is not a CFL because here you need to do multiple comparisons. More than one comparison you need to do. You need to compare this. Once you are done comparing them, then you cannot compare with this C power n because nothing is left. So you need to do multiple comparisons. You need to do multiple comparisons. You need to compare this comparison, this comparison. But you can your PDA cannot do multiple comparisons because once you are done comparing these things, now there is nothing left for comparison with C. So that's why PDA cannot do this. These things are clear or not? Aditi, Gayatri, let me know. Any doubt? Any doubt in these things? If there is any doubt, then you can ask. Let's see the next question. W belongs to A star. See, now our alphabet is unary. Our alphabet is unary. Okay, you can see. Now tell me, this WW, is this regular, DCFL, CFL? Tell me. Try this question. Use your brain, use your creativity. Tell me WW. The W belongs to A star. Basically, our alphabet is unary alphabet. Tell me this WW, is this regular, DCFL, CFL? Tell me. Why this is regular, Aditi? Yes, of course. Every regular language is DCFL, every DCFL is CFL. But my question is why this is regular? No, no, this is not finite. See, our alphabet is finite, but this WW is not finite. Like, see, this WW is not, this WW language, this is not finite language. For example, your alphabet is A, okay, W belongs to A star. So, for example, this language WW will have epsilon, this will have double A, this will have 4A, this will have 6A, 8A, 10A, and so on. This is an infinite language. This is not a finite language. This is a infinite language. The language is infinite. Let me tell you why this is regular. This is indeed regular, but no, this is regular. See, W belongs to A star. Basically, our alphabet is unary alphabet. You can see our alphabet is, our string is over unary alphabet. Our string is over unary alphabet. What is our language? Our language is WW. Basically, every string is of the form WW, where W belongs to A star. This is our language. One thing you can notice, just use your creativity and try to notice what is this language. This language actually is saying that you have two half. In this first half you have W, and that W is basically all A's you have, and then you have this half. Here you have, if basically here you, let's assume you have A power M here, then in the second half also you have A power M. What is this? This is A power 2M. Basically your language is just number of A's are even. You can say that your language is nothing but number of A's are even. So when your W belongs to A star, when your W belongs to A star, when you have unary alphabet, then this WW is nothing but, number of A's are even. This is your WW. Is this clear? You can see, because your W is number of A's. So WW means A. This is A power M. Let's assume this is A power M. Then this is also A power M, and this complete thing will be A power 2M. So you can say that your language is this language, number of A's are even, and this language is regular, number of A's are even. We have already constructed DFA for this type of languages. Number of A's are even, length of string is even, length of string is odd, number of B's are odd, number of B's are even, length of string is divisible by 3, length of string is divisible by 4. Okay, all these things we have already done. For all these languages we have already constructed DFA, we have already constructed NFA for all these languages. So all these type of languages are regular languages. For example, this A star, B star, this is a regular language. For example, substring languages are regular languages. For example, your in your string AB is a substring. Your string contains AB as a substring. So these substring languages are regular languages. Okay. So all these length languages are regular languages. For example, length is odd, length is even, length is divisible by 3, length is divisible by 10. All these languages are regular languages. Every finite language is regular language. Okay. Sigma star is regular. We for those languages we have already constructed DFA. If you remember, for those languages we have already constructed NFA. For all these languages we have already constructed DFA, NFA. So all these languages are regular. Okay. So basically, actually, in GATE exam, you need to do a lot of practice, because in GATE exam they can ask you, like, they can make their own language, and you need to just check out. You need to do, with practice it will come. When you do a lot of practice, then it will come. Whether a given language is regular, DCFL, CFL, all the tips and tricks I have already told you. There is nothing left from my side. I have already told you all the tips and tricks. For example, when there is a single comparison, then it is CFL. When there is double comparison, then it is not CFL. When there is push and pop are clear, then it is it is DCFL. When push and pop are not clear, then it is not DCFL. When there is unlimited comparison, unlimited matching, unlimited counting, then it is not regular. Okay, so all these things we have seen, but of course it will come by practice. When you do a lot of practice, then it will come. You will be able to find out whether the given language is regular, DCFL, CFL, all these things. They will come by practice. So you need to do a lot of practice. What you can do, you can try to solve the previous year GATE questions. And when you solve the previous year GATE questions, then wherever you get the doubt, we will discuss. We will take a discussion session, as I told you, for discrete mathematics, for TOC, for both of these subjects. We will take some discussion sessions. Okay. In those discussion sessions you can ask your doubts. But before that you need to solve the previous year GATE questions. I have already provided you 3 PDFs. I provided you. Those are called Go PDFs. 3 PDF. In those 3 PDFs, PDF P1, PDF P2, PDF P3, In those PDF, all the for all the subjects you have gate questions, you have gate and TIFR questions in those PDFs. So you can just go to the discrete mathematics section, and in that section you can try to solve all the discrete mathematics questions of the previous gate and previous TIFR exams. Wherever you have doubt, you can ask me on WhatsApp immediately, or you can note it down and you can ask me in the discussion session. Okay, I would prefer that you ask immediately on WhatsApp. You can ask me, or in the next lecture you can ask me, or in the discussion session you can ask me. Similarly for the TOC subject also. Okay, and actually there is one good thing about these PDF. When you will go to when you will go to the discrete mathematics or any subject, then you have this question. On this question, when you do the right click, this after right clicking you can open this question in a new tab. Then this gate overflow website will open. This website, gate overflow website, will open. This gate overflow website is basically, this has solutions of all the gate questions. Here you will find around more than 50,000 questions. You will find here with solutions, with detailed solution. Okay, so you what you can do, in whichever question you have doubt, so you can right click, you can open a new tab. There you will be redirected to the gate overflow page. In that gate overflow page, for that question you can read the answer, read all the answers, all the discussion, all the comments. You will get every concept. Okay, Aditi, all these PDFs, every material is being shared in the drive. In the drive you will find, in the drive every material is there. Okay, I have put all the material in the drive. You can find out, or you can ask your friends. You can ask Gayatri, Sanjeev. They will provide you this go PDF. In these three PDFs you have all the previous year gate TIFR question. All the questions are there. In these three PDF you have all the questions. And for the solution, what you need to do, just right click on the question, go to the new tab, and there you will find the solution, detailed solution. Many solutions you can have. So go through all the solutions, all the discussion, all the comments. You will get the answer basically. Okay, even after doing that, if your doubt does not get resolved, then you can ask me in the solution session, or you can ask me on the WhatsApp. Okay, so I think this is enough for today. And in the next lecture, what we will do, we will see the closure properties of CFL, we will see closure properties of DCFL, and we will take some more examples, how to find whether a given language is regular, DCFL, CFL. All these things we will see. Closure properties and detection of language, like detection of regular language, detection of